Welcome to our first semester zoology course. Today, we are diving into a fascinating and life-saving topic, insect vector management strategies. If you have ever wondered how public health officials stop massive outbreaks of diseases like malaria or dengue, you are in the right place. We will explore not just the biology, but the actual mathematical tools used to save millions of lives. Let us get started. Before we look at the science, let us think about a burst water pipe in your living room. You could grab a mop and frantically try to soak up the water, but the most logical first step is to find the main valve and turn off the water supply. In public health, treating sick patients with medicine is like mopping up the water. Insect vector management is the equivalent of turning off the valve. By controlling the insects that carry diseases, we prevent the pathogens from ever reaching human hosts in the first place. This proactive approach is the absolute cornerstone of global health initiatives. Now that we understand the proactive mindset, let us define what this looks like formally. Insect vector management is a systematic, science-based approach to reducing or eliminating populations of disease-carrying insects. Modern science relies heavily on something called integrated vector management, or IVM. This is a rational decision-making process designed to optimize our resources. Instead of relying on just a single method, like spraying chemicals everywhere, IVM combines multiple strategies to attack the vector from different angles. By layering these methods, we create a completely hostile environment for the vector at every single stage of its life cycle. Building on the idea of integrated vector management, let us look at the specific tools in our toolkit. We have cultural control, which involves changing the environment, like removing stagnant water where mosquitoes breed. Then we have mechanical control, which uses physical barriers like window screens or bed nets. We also use chemical control, applying specific insecticides carefully. Biological control is fascinating. It involves introducing natural predators or pathogens that specifically target the insect. Finally, behavioral control manipulates the insect's habits using traps or even genetic modifications. Using these together is what makes our defense so incredibly strong. You might be wondering, why go through the trouble of combining all these methods? Why not just spray chemicals everywhere? Understanding this is absolutely critical. Vector-borne diseases account for over 17% of all infectious diseases globally. If we relied solely on chemical insecticides, insects would rapidly evolve genetic resistance, creating dangerous supervectors that we cannot kill. Furthermore, excessive chemical use damages local ecosystems, killing beneficial insects like bees and contaminating our water supplies. Integrated management ensures we use the absolute minimum necessary chemicals while maximizing environmental and biological tools, protecting both human lives and our planet. Having established our core strategies, we now need a way to measure their potential impact. To truly understand how these management strategies work, we must look at the mathematics of disease transmission. Entomologists and epidemiologists use a powerful mathematical model known as vectorial capacity. This concept tells us the average number of potentially infective bites that will be delivered by a vector population feeding upon a single infectious host in one day. By calculating this specific number, we can pinpoint exactly which management strategy will have the most massive impact on stopping a disease outbreak before it starts. This brings us to the mathematical heart of vector management. The formula for vectorial capacity, C, equals m times a squared times p to the power of n, all divided by the negative natural logarithm of p. Let us break this down. C is the total number of new infections generated per day. The variable m stands for the density of female mosquitoes per human host. The variable a represents the daily biting rate on humans. Notice that a is squared. This means if we reduce the biting rate, the disease transmission drops exponentially. The variable p is the daily survival rate of the insect, and n is the incubation period of the pathogen. Let us see this formula in action with a concrete example. Imagine a rural village facing a malaria outbreak. Entomologists find there are 10 mosquitoes per person, so m equals 10. The daily biting rate, A, is 0.5 bites per day. The survival rate, P, is 0.8, and the pathogen takes 12 days to incubate, so N equals 12. We want to find the initial vectorial capacity. We substitute these values into our equation. We square the biting rate of 0.5 to get 0.25 and raise 0.8 to the 12th power. After performing the arithmetic, we find the initial capacity is approximately 0.77. This means every infected person generates merely one new infectious bite per day. Now that we have our baseline, let us see what happens when we introduce insecticide-treated bed nets. These nets act as a mechanical and chemical barrier, lowering the biting rate, A, from 0.5 down to 0.1. We plug this new value into the exact same formula. Because the biting rate variable is squared, our new value of 0.1 becomes 0.01. When we calculate the final result, the new vectorial capacity drops drastically to approximately 0.03. A 5-fold decrease in biting resulted in a massive 25-fold decrease in disease transmission potential. This proves mathematically why bed nets are so incredibly effective. So, we have proven that interventions like bed nets work in theory. But how do we measure success in the field? Another crucial aspect of vector management is evaluating the actual success of our control agents, like spraying larvicides in a pond. When we spray a pond, we will inevitably find dead mosquito larvae. However, we must remember that some larvae would have died naturally anyway, due to predators or weather. To scientifically prove that our management strategy actually worked, we must correct our data to account for this natural background mortality. We do this using a famous mathematical tool called Abbott's formula. Let us look at how Abbott's formula is structured. The formula states that E equals m sub t minus m sub c divided by 100 minus m sub c, all multiplied by 100. Here, the variable E represents the corrected efficacy percentage, which tells us the true killing power of our intervention. The variable m sub t represents the observed mortality percentage in our treated area, like the pond we sprayed. The variable m sub c represents the natural mortality percentage observed in an identical, untreated control pond. By subtracting the natural mortality, we isolate the exact percentage of insect deaths caused strictly by our management strategy. Let us apply Abbott's formula to a real-world scenario. A public health team is testing a biological control strategy using bacteria to kill mosquito larvae. In the untreated control pond, they observe a natural mortality rate of 15%, so m sub c equals 15. In the treated pond, they observe a total mortality rate of 83%, so m sub t equals 83. We place 83 and 15 into the numerator. In the denominator, we subtract 15 from 100, which represents the maximum possible survival rate. Dividing 68 by 85 gives us 0.80. Multiplying by 100, we get a corrected efficacy of 80%. The biological agent itself killed exactly 80% of the population. Now that we have calculated the efficacy of our tools, let us visualize how they all fit together. This diagram illustrates the integrated vector management approach applied to a mosquito's life cycle. Notice the 4 distinct stages in the center: egg, larva, pupa, and adult. Around the outside, you can see how different strategies target specific vulnerabilities. Environmental management, like draining water, attacks the egg and pupa stages. Biological control targets the aquatic larvae. Chemical control is used against the flying adults, while mechanical control, like window screens, blocks the adults from feeding and laying new eggs. This diagram perfectly captures why a multi-layered defense is so effective. We have covered a lot of ground today, so let us summarize the most important ideas. First, integrated vector management is a multifaceted discipline that combines cultural, mechanical, chemical, and biological tools to attack vectors at every life stage. Second, relying on this layered approach is essential to prevent genetic resistance and protect our ecosystems. Finally, we learned that mathematics is just as important as biology here. Models like vectorial capacity allow us to strategically plan our interventions, while Abbott's formula lets us rigorously measure their success. By mastering these strategies, we empower ourselves to break the chain of disease transmission and save countless lives. Great job today!